Um, Hello and welcome. My name is Daniel Herring, and thank you for coming today to my talk on my work, Dynamic Multi-Objective Optimization using Evolutionary Algorithms. There are three key topics I'm going to be discussing today, including an investigation of the frequency and severity parameters in dynamic benchmark problems, together with trying to improve the reproducibility and enable easier comparisons with future experiments. Secondly, I'll be addressing a limited provision of combinatorial problems in the dynamic multi-objective space and defining problem instances with contextually justified dynamic changes and trying to find solutions to these problems. Finally, introducing the idea of dynamic problems with multiple independently changing dynamic components and attempting to navigate the complex instance space that's generated. First, however, a brief introduction on dynamic multi-objective optimization and evolutionary algorithms to get us all on the same page. Multi-objective optimization problems are problems that contain multiple conflicting objectives that provide fitness scores based on a vector of decision variables. Within the objective space, we can achieve a set of solutions that represent the best trade-offs between the two objectives or more objectives. They lie on a boundary called the Pareto optimal front, and the decision vectors of these solutions comprise the Pareto optimal set. When we consider a dynamic problem, we introduce a dependency on time such that the Pareto front or the Pareto set may change over time. It could also be both or neither. Don't know why that didn't play straight away. I'm sure many of you are familiar with evolutionary algorithms, so I won't spend too much time here. They exploit the natural principles of survival of the fittest and natural selection by iteratively producing solutions, by combining the ones you already have and then comparing the new and current solutions and selecting the best set based on their objective values or some other selection criteria. EAs are typically employed when the search space of possible solutions is not innumerable, as they can efficiently navigate to good solutions over relatively small number of iterations or generations. Now that we're at least a little familiar with dynamic multi-objective optimization and with evolutionary algorithms, I'm going to talk through each of the three distinct chapters of work, covering the motivations, methodology, and contributions from each. Firstly, investigating the frequency and severity parameters that control the nature of dynamic change events within these problems. This is an almost entirely ignored topic, and previous works experimenting on dynamic multi-objective optimization benchmarks either use a narrow range of parameters, settings inconsistent with other works, or provide no justification for the values selected. This obviously results in a limited applicability or relevance of their conclusions, difficulty making comparisons with other works, and poses questions about the strength of claimed algorithm performance, for example. A systematic, comprehensive, and reproducible methodology is provided, and a baseline for future comparisons is established using well-known algorithms and simple dynamic response mechanisms. Secondly, to address the limited availability of multi-objective combinatorial benchmark problems that contain realistic dynamic characteristics, a number of contextually justified definitions for the dynamic bi-objective traveling thief problem are given. Suggestions for effectively finding good solutions using an exploitation of the problem knowledge and a comparison with established heuristics for the static problem are given to provide a meaningful performance basis for these instances. Finally, to continue the expansion of the dynamic multi-objective problems, which incorporate characteristics of realistic systems, definitions for multi-dynamic problems are investigated for both continuous and combinatorial problems. An investigation of the observable motifs in algorithm performance across different frequencies and severities within these multiple components serves as an introduction and a first step towards informed experimentation on this novel class of dynamic problems. So generally, there are a number of fields of research within dynamic multi-objective optimization, or DMO, that have received plenty of attention over the past 2 decades. These can be grouped into algorithms, benchmarks, and performance measurements. real-world applications, as well as mechanisms that surround adaptability of response mechanisms and the detection of changes are also popular topics. However, a key aspect of problems with dynamics is the parameters that control how often and how big the changes that occur, And as a topic, this has been largely ignored. To investigate this, we can propose one of the key research questions around improving the understanding of these impacts in a way that enables meaningful outcomes that can inform future experimentation. Similarly, the continuous space has received most of the attention in terms of dynamic multi-objective benchmark problems. So proposing a combinatorial example that incorporates justifiable and realistic dynamics is a helpful contribution to the field. Extending the range of characteristics captured by test problems, including multiple dynamic components, provides a novel problem class to investigate. Let's look at the frequency and severity of the dynamic changes first. We can pose the research question as such: how can we understand and explain the impact on algorithm performance of the parameters controlling dynamic changes, these being the frequency and severity, in benchmark dynamic multi-objective problems, and through facilitation of a reproducible experimental methodology, where the results can be replicated and easily compared in future investigations, make recommendations, both generally for experimental design and specifically based on the observed impacts of the frequency and severity on the different problems. The frequency and severity parameters are key to defining the nature of changes. The formula shown here is the most commonly employed strategy for controlling these factors. Using parameters for the frequency, the tau t, and the severity nt, as shown in the formula. A larger value of nt results in smaller changes as the difference between successive t values is lower. Larger values of tau t result in a longer time delay between changes. Naturally, we can imagine that a high frequency, high severity instance of a problem may pose a different level of challenge than an instance with low severity and low frequency. Traditionally, the selection of these parameters has been inconsistent, sporadic, and often unjustified, as I'll illustrate in a moment. Crucial to the cohesive progression of research in this area is the ability to compare results and reproduce instances and data from experiments. This forms a key motivation of the investigation of these parameters. Using the references list from a very recent survey on dynamic multi-objective optimization, we can observe how frequency and severity parameters have been selected in previous works. The scatter plot shows that the combinations of frequency and severity parameters employed are wildly varying, and there's generally a non-cohesive approach to selecting combinations. There are single cases of frequency 300 being used and a severity 1 being used, but also a selection of combinations inconsistent with any previous work. If we zoom into the denser region, we still see that there's a range of values of parameters employed with no strategic selection in the sample as a whole. If we look at the prevalence of specific values that have been used, we can see that there are commonly adopted values for frequency and severity, largely due to infinite influence from foundational papers in the area. A severity of 10 and frequencies of 5, 10, and 20 are the most commonly used combinations. Notably, the same parameter values are usually applied to all benchmark problems in each study, regardless of the potential difference in impact on the problem. When we consider further the number of combinations applied to benchmark problems, i.e. the number of dynamic instances considered, most commonly a single combination is employed. This severely limits the applicability of conclusions about algorithm performance if you're examining just a single instance within a possible dynamic instance space. This demonstrates the ignorance to common sentiments in the literature for a variety of frequency and severity combinations to be examined, which is commonly quoted. Instead, we need a more comprehensive approach to ascertain the impact of these different parameter combinations and determine the importance of informed selection for experimentation, as well as correctly conditioning conclusions. Pairwise assessment of combinations in this range will help build a clearer picture of the variation across the possible dynamic instance space. And it also enables us to generate a baseline of performance for future comparisons. So we can establish these baselines in the context of performance of some well-known static algorithms, meaning multi-objective evolutionary algorithms not originally designed to cope with problems that have dynamic changes. These well-known algorithms, the NSGA2 and 3 algorithms, SPEA2 and MOEAD in particular, are often employed as comparison methods for novel dynamic algorithms to try and provide some kind of context for their results. However, the true potential of these algorithms is not reported across the possible dynamic instance space, and very few combinations are usually examined. Similarly, they're often augmented with simple response mechanisms, including the addition of random or mutated solutions, meaning solutions that have undergone a small change, or a destructive reinitialization of their population, known as a random restart. Therefore, using these algorithms and their augmented variants, we can establish a comprehensive and comparable baseline of performance across the frequency-severity parameter combination instances. We can ascertain the relative benefit of the simple response mechanisms and provide insights into parameter selection on a problem-specific level. These experiments were carried out using the specially constructed DTTP, or Dynamic Parameter Testing Platform, for which the GitHub page is shown on the screen. Inspired by the existing PlatEmo platform for static multi-objective problems, here we can apply algorithms and variants I mentioned previously to dynamic benchmarks with a variety of parameter settings. We can also perform the pairwise parameter testing, recording the performance of the algorithm during each dynamic interval of a problem and representing this as a heat map or a grid across these combinations. The motivation for providing the tools used to generate my results is to try and address the transparency and reproducibility that are largely missing from the dynamic optimization community. Feedback from anyone interested in using this would be greatly received. So to summarize the experiments conducted, to answer that initial research question, the 4 algorithms and each of their variants are examined on each of 17 benchmarks from a variety of well-studied and more recent suites across a range of 630 combinations of frequency and severity parameters. Within each run of an algorithm, the performance is measured as the hypervolume difference, meaning the error between the optimal obtainable hypervolume and that achieved by the algorithm at the end of each dynamic interval, and then averaged over every interval in the problem. A total of 30 changes are employed in every instance and 5 repetitions for each instance. As you might imagine, this produces a lot of data, but we need this to generate the more comprehensive baseline than the previous convention for choosing frequency and severity shown before. The best way to visualize this, as I already alluded, is a heat map of the performance across the dynamic instance space, which we generate by combining different frequency and severities together. So an example is shown here for the NSGA2 algorithm with no additional response mechanism on the DMOP2 benchmark instance. Each cell represents the measurement for a single combination of parameters, and the color bar to the right of the heat map shows the range of the hypervolume difference values achieved. A value of 0 here indicates the perfect hypervolume attainment in every dynamic interval of a problem instance, while the darker gray shows a poorer achievement. As a reminder of what these results are hoping to display, there are 4 things we can focus on. Determine the impacts of frequency and severity on different problems, compare the different static algorithms and the simple dynamic responses, and contrast these observations with previous usage of frequency and severity parameters. So a typical patterning of performance we see on some of the problems is shown in these 2 heat maps. In the top right of each plot, we see this lighter region, white cells indicating perfect hypervolume attainment. And this extends to the left and down as the frequency gets lower and the severity gets higher. The good performance drops off. The hardest instances are in the bottom left here. Ooh. In the bottom left here. These have the rapid change events with high severity, and the performance of these static algorithms cannot handle these instances, but the performance drops off long before these. Other problems feature a much smaller good range of performance coverage. If it will work, there we go. And they're generally much harder for the algorithms. We can see a much smaller white region in the easier instance space region. Some of the problems also have a non-uniform patterning. This last group highlights that the frequency and severity parameters have different impacts on different problems. And sometimes the increase in severity or frequency can have a non-intuitive impact on algorithm performance. This reinforces that selection of these parameters should be careful and informed. Some of the investigated problems have no challenging combinations for the examined algorithms. Each column here is one of the algorithms, and each row is a different problem. The mostly white cells indicate that most dynamic instances of these problems can be effectively handled by static algorithms, and therefore should not be used to evaluate novel dynamic algorithms. The algorithms perform similarly for many of the problems, with MOEAD in the third column, a decomposition-based algorithm performing slightly better across the space than the other dominance-based algorithms. NSGA3 in the second column performs slightly worse on most problems too. Because there are some differences, multiple baseline comparison algorithms could be used to guarantee confidence when making claims about novel algorithm performance. In terms of the simple dynamic response mechanisms, neither the diversity introduction methods, that is adding random or mutated solutions in the second and third columns here, provided any major observable difference to the performance of the static algorithms. The population prediction strategy also provided minimal improvements. If we look at the random restart method, however, shown on the right column of each pair, with the default algorithm shown on the left in each pair, we can very clearly see that it removes the majority of good performance coverage, even for the problems we established as too easy on the previous slide. This highlights that the random restart method should not be used. Here's some more examples. The random restart method should not be used as a comparison method over the use of an unmodified static algorithm. Using the random restart as your baseline may inflate the reported performance of a novel algorithm and may weaken conclusions on its ability. And so using a random restart should be considered very carefully. Oh, here's some more examples. So we lose all of the good performance in the white region when we randomly restart. When we look at some examples of how commonly used combinations, so these are the combinations I showed earlier from the literature, the black crosses on the heat maps, where we see where they lie on the performance heat maps, we can see if the combinations of frequency and severity are used in the regions of good performance. When this is done, they don't provide any meaningful benefit to the field generally, as these instances can already be handled by simple non-dynamic algorithms. To clarify, testing a novel algorithm on a combination shown by the black cross here will yield little performance improvement over the baseline. However, targeting the algorithm at a novel algorithm at the yellow cross, an instance that's difficult for the static algorithms, or at the red and orange crosses on the boundary of mediocre performance, will improve the overall coverage of good performance across the possible dynamic instance space for these problems. As I mentioned before, some problems should be avoided altogether, as these can be effectively handled by the static algorithms, regardless of the frequency and severity settings. They could still be used to verify basic capability of novel algorithms, however. We can make a number of general recommendations and more specific ones based on the specific problems. These recommended combinations are shown in the table. The frequency and severity parameters should be selected intelligently and with justification based on the benchmarks being examined. When examining the capability of a new algorithm, a comprehensive or stratified approach to selection is encouraged, since the performance coverage of the instance space is variable. Multiple baseline comparison algorithms should also be used. Alternatively, in combination with the baseline performance established here, specific targeting of combinations that the static algorithms cannot handle would be a suitable experimental contribution. We've answered the initial research question by visualizing the impacts of the frequency and severity parameters in the context of performance of static algorithms, as well as the performance of their basic dynamic modifications. We've done this across a comprehensive range of combinations as well. This has been produced using a platform devised to facilitate the reproducibility of these results. We've also made specific and general recommendations for using dynamic multi-objective benchmark problems in future works. Okay, so now we'll move on to the dynamic traveling thief problem. The proposal of the dynamics here provide us with a useful testing platform for multi-objective optimization in a combinatorial domain with dynamics. I'll explain how it's possible to observe and then exploit the varying contributions of different initialization strategies for this problem in order to provide a response mechanism to the proposed dynamic changes. A comparison to heuristics adapted from the static traveling thief problem, a consideration of multi-population models, and an evaluation of the frequency and severity impacts is also introduced. Firstly, however, I'll begin with an introduction of the existing non-dynamic traveling thief problem. So the traveling thief problem was initially defined in 2013 by Boniardi et al. And has been extensively investigated by the optimization group in Adelaide, who I'm sure many of you are familiar with. It is a problem, it is a well-designed problem that combines the well-known traveling salesperson problem with a knapsack problem. The thief must complete a tour of all the cities, but may also collect items along the route that have a value and a weight associated with them. The bi-objective version of the problem has the time taken to complete the tour and the profit of the collected items as the competing objective functions. The two components of the problem are interconnected, as the weight of the collected items reduces the travel velocity and the profit of the items decays over time. Generally, this problem represents a controllable benchmark environment that encapsulates the complexity of more realistic systems, which makes it the perfect candidate for transformation into a dynamic problem. Existing dynamic multi-objective optimization problems in the combinatorial domain are limited, with attempts at defining dynamic multi-objective knapsack problems and dynamic multi-objective TSP problems, so traveling salesman problems, and some of the FDA benchmark set having little utility or unjustifiable dynamics or some other limitations to them. This allows us to state our research question as follows. Given the lack of existing DMOP benchmarks in the combinatorial domain, how can we justifiably incorporate dynamics into existing problems, this being the traveling thief problem, to reflect characteristics observable in real-world systems? This will be clear in the next few slides, and then attempt to find solutions in these new instances. An attempt to introduce dynamics was proposed in 2020 by Sachdeva et al. However, there, a contextual justification is not presented for the proposed dynamics, and between intervals, the total number of cities and items changes. There's also limited comparison with other methods, so the results are somewhat out of context. The single objective problem was also considered there. The dynamic traveling thief problem problems proposed here provide us with a bridge between the simplistic dynamic TSP and knapsack problems and the exact and complex real-world scenario. We can examine a variety of scenarios with a range of dynamic changes to ascertain mechanisms which can provide good results on these complex interconnected problems before deployment into the real world. The first type of novel changes is a change in the city location. Here we change the X and Y coordinates of the cities as shown in the diagram, which alters the state of the TSP component of the problem. The indexes are randomly selected, but the pattern of changes is recorded so that multiple runs can be performed on the same pattern of changes. We can use the traveling thief problem as a model for logistics or fleet management scenarios, i.e. goods delivery vehicles collecting items to return to a depot, or waste and rubbish disposal scenarios. The proposed dynamic changes can be easily justified within this model too. This type of change simulates a change in the pickup location that could be a store or a depot change to an alternative location, and it could also be representing a road closure or a routing change. The severity of change used here is the number of cities that change location. However, this could be modified to be the magnitude of the displacement, or mainly just the magnitude of the displacement. An important feature of the proposed dynamics is that the number of cities remains constant throughout the dynamic intervals of the problem, removing some issues in comparability that might arise with altering the number of active cities. We use a constant frequency and severity within each instance. However, varying the frequency and severity throughout the optimization is another interesting topic that requires investigation. The second type of dynamic changes is in the availability map. This part of the problem describes which items are at which city. When a change occurs, randomly but reproducibly, selected items are swapped between random cities. Contextually, this amounts to a depot or a store changing its stock or collecting the same item from a different location. The severity here is the percentage of items that, so here's the swapping of these two items. Contextually, this amounts to the stock switching between two stores. The severity here is the percentage of the items that get swapped. So the final type of dynamics proposed are within the item values themselves. Here, the profit is associated with a percentage of randomly, again reproducibly selected items undergo a change. There's also an additional parameter here which fixes the magnitude of this change, but the sign is not fixed. In context, this represents the realistic changes that we see due to inflation or depreciation in value. Now to try and find some solutions to these novel instances I've proposed. A variety of exact and approximate methods have been employed to help find solutions to the traveling thief problem without dynamic changes. And across many of these, some exploitation of knowledge about the problem is common. For example, employing TSP solvers and knapsack solvers to provide the starting point for heuristics tackling the interconnected traveling thief problem. Naturally, a comparison of different initialization and initial set construction methods were compared, and the contributions of an aggregated, non-dominated set reveals that navigation to different regions of the objective space is facilitated by different initialization strategies. This figure shows that for a smaller instance, here with 52 cities and one item per city, that the unique contributions are different based on the construction of the initial set. Here, each point is a solution, and the colors correspond to the labels in the legend. The first letter of each label is the method for constructing the initial population's TORs, S for solver, G for greedy, and R for random. The second letter is how the knapsack solution, and therefore the packing plan, was constructed. As the instance size increases, here to a 783 city problem, again with one item per city, the contributions in the same allotted time from randomly generated solutions are not present. So those are the ones towards the right-hand side of the chart. Population seeding has also been addressed for multi-objective problems, or multi-objective evolutionary algorithms, And therefore, this provides a logical opportunity to determine the effectiveness of seeding the population after changes with differently constructed solution sets. This strategy is named as the responsive seeding approach, or responsive seeding algorithm, as we are responding to the dynamic change events by seeding the population with information known about the components of the new problem state. In this simplified flowchart of an evolutionary algorithm from before, when a dynamic change event occurs, we resolve the components of the problem, the TOR and the knapsack components, and then we can mutate this and construct some additional solutions to generate an entire population. Then, instead of the algorithm generating its offspring as normal, we provide it with this crafted solution set filled with the solver information. It then operates as normal until another dynamic change happens. To evaluate the effectiveness of different methods of constructing this responsive solution set, we can examine a number of different problem instances. These are shown on the radial ticks of the plot, with the number of cities in the TSP component shown first, and then the number of items per city and the weight profit distribution indicated by the letters A, B, and C for 1, 5, and 10 items per city. The colored line represents the median ranking across 10 patterns of dynamic changes of the hypervolume measurement in 30 repeats. Higher numbers for the rank are better here for clarity. We can also visualize this for the one shown at the moment is for the city location changes, but we can also visualize this for so here's a summary of the how the measurements were calculated. For the availability and the item value instances, the plots are shown now. This color specifically corresponds to just using solver-based information to construct that seeding population. However, we also tested more diverse methods involving the mixing of random, greedy, and all three construction methods. We can see that the most diverse method, which combines all three types of solution construction in every combination, provides the best coverage of the larger instances, whereas the smaller instances are more competitively handled by a number of different methods. We extend this investigation to consider a comparison to heuristics known to be good for the static traveling thief problem. Since random initialization of the problem was shown to not be competitive with exploiting knowledge about the problem components, adapting these methods makes more sense than using a dynamic algorithm that may not be able to handle the complexity of the traveling thief problem generally. The S5 heuristic and two versions of the MAT-LS algorithm were reproduced from their descriptions in the respective papers, as there wasn't code readily accessible for either of them. As the comparison methods were not designed to produce and maintain a population with good coverage of an approximated Pareto front, we must instead focus on the optimal values achieved in the extremes of each objective, the maximum profit and the minimum TOR time achieved in each iteration of each algorithm. The profiles here indicate that for this example problem, the constructed seeding algorithm maintains a good profit and good TOR solutions at the same time compared with the other methods. In order to summarize these results, the comparisons we provide through a statistically driven comparative analysis, which respects the complex behaviors in dynamic problems. Again, the instance names are given radially around the plot, and the algorithm name is given just above it. The top and the bottom plots respectively show the proportion of generations in which this particular method achieves solutions with a significantly higher profit on the top or significantly lower times. And the colors indicate how many of the other methods the significant improvement is over, with corrections for multiple comparisons applied. The darker shade indicates significant improvement over all three of the other methods. The mid-tone is over two of the other methods, and the lightest shade is for significant improvement over just one other method. If we look at all of the methods, we can see that the S5 heuristic handles the majority of dynamic instances the worst, and the seeding algorithm, the MC method, has the best coverage of significant improvements across the examined problems. These results are shown specifically here for the location change dynamics. So to summarize so far, before I continue on to the last two parts of this section, we've seen the contextually justified definitions for three different flavors of the dynamic traveling thief problem. We've observed the differences in contribution of different initializations to the achieved set of solutions or the achievable set of solutions. The exploitation of this as a dynamic response methodology has been evaluated and compared to adapted heuristics from the static traveling thief problem. I'll now show the development of this into using multi-population models for isolated and directed evolution towards specific objective space regions, and also at the frequency and severity in these dynamic traveling thief problem instances. Because there was an observable difference in the outcomes when using the different initialization methods, one way to develop this idea is to allow multiple populations to focus on finding solutions in different regions of the objective space. The three topologies tested are on the screen now. The first is just the default single population model, same as before, where finding solutions to both objectives is equally important. The middle model has two additional subpopulations, with each of these having an additional selection bias for better solutions in each of the objectives. When taking measurements, the aggregated non-dominated set is taken across the three populations. The final model, whilst looking a bit more complex, has two simple mechanical changes. The first is a mixing population in the center, and the second is the migration of solutions between these populations. The numbers indicate the frequency and the first occurrence of migration events in generations. There is frequent bidirectional migration from the focused populations to the mixing population in the center, and less frequent unidirectional contribution to prevent interference in those focused populations. So unidirectional contribution towards the principal population on the right. The mixing population also contributes to this on a slower timescale. Experiments were conducted in conjunction with the different seeding methodologies, equated and non-equated global population size of these models, and with respect to resolving the Tor and knapsack components between dynamic intervals. I can't go too much more into the details due to time, but I can summarize the key results. So firstly, the hypervolume measurement profiles on the left illustrate for three example problems with city location changes, the relative success of the three different topologies. The MI model, the one with migration, outperforms the others, most evidently on the B and C type instances. These ones have more items per city. The pairwise comparison in the table of the generation-wise significant improvements between the different models highlights the effectiveness of multi-population models and multi-population models with simple migration events compared with a single population. For example, in the C-type problems, in the bottom third of the table, the MI model versus the multi-population with migration versus the single population, the center pair of values, in at least 95% of generations, the migration model achieved significantly higher hypervolumes. To continue the investigation of the dynamic traveling thief problem instances, we can look at the impacts of the frequency and severity as before. There are some key differences to the continuous problems that we examined before, however. As the Pareto front for the traveling thief problem at any dynamic state is unknown, this limits the absolute claims we can make. We can, however, determine the relative impacts and determine the scale of the impact of altering these parameters. Further solutions are needed generally to effectively evaluate dynamic multi-objective problems with unknown Pareto fronts, but we can still achieve useful insights with the measurements we can currently take. Shown in the figure is the 52-city A-type problem with a severity of change 3 and a varying frequency. The x-axis shows the change index, with 0 being the measurement of hypervolume taken just before the first change, where the algorithm has had a standard 50 generations to warm up, if you will. Each of the different shades of gray indicates a different frequency between the same change events indicated by the indexes on the x-axis. The darkest gray measurements are taken after 20 generations and the lightest after 200 generations. Effectively, the lighter the shade of gray, the more time the algorithm has had to find better solutions. So we expect the hypervolume measurement to be higher for the lighter gray than for the darker gray. We can see that each group has a positive trend, and at higher severity, shown here, the achieved hypervolume values, so the maximum value on the y-axis, are lower overall. Although somewhat messier than the heat maps for the continuous problems, we can confirm that similar trends of lower frequency and lower severity persist in the combinatorial problems too. As in, we achieve better performance in the top right region of the heat maps. More work is needed, however, to allow for the same comprehensive insights to be given for the combinatorial problems. So we've covered parameters and problem gaps in combinatorial dynamic multi-objective optimization. Now let's look at what comes next. Introducing novel problems that incorporate additional realistic characteristics. Multi-dynamic problems. The aim here is to propose definitions for candidate benchmarks and determine the key challenges for this type of problem. By no means are these concrete and the not comprehensive conclusions. Okay, sorry, I just got distracted by the chat. These aren't concrete or comprehensive conclusions, only recommendations based on observing both combinatorial and continuous problems. Sorry, I skipped one there. So we might expect a real-world system, such as maybe a power grid, to have a fluctuating demand and supply, but we do not expect these to vary at the same frequency or with the same severity. We could also consider a logistic scenario similar to the proposed dynamic traveling thief instances, where more than one type of dynamic change is occurring, but on separate timescales. We published at CEC in 2019 on an investigation of this type of dynamics in 2 and 3 objective benchmark functions. However, in other literature, there have been some allusions to this kind of problem. For example, Yazdani et al. In 2020 specifically said that multiple frequencies should be considered. There's also other works which deal with slightly different concepts of different frequencies and asynchrony. Almendinger and Knowles have looked at resource constraints and evaluating different objective functions at different times. And Ake in 2013 suggested asynchronous updating of the objective functions for artificial bee colony algorithms. So let's try and explain a little more about the problems themselves. To be specific,
Dan, sorry, just before you go on, you're only going to have about 5 or 6 minutes, okay?
Yep, so okay. There's not too much left. To be specific, we're talking here about there being multiple dynamic components within a single problem. In the figure here, for example, from the CEC paper, there's a Pareto front offset and a change in density of solutions as separate dynamic events. Each dynamic component in the problem will have its own t-value, and therefore it can have its own frequency and severity parameters, and each t-value is likely to impact the problem in a different way. The possible combination of parameter values, as in the previous investigation, results in a large possible dynamic instance space to examine, and this is the first challenge. So our research question, multiple independently changing dynamic components have not really been represented in problems previously. How can we apply a similar methodology to both continuous and combinatorial problems to determine the key features and challenges for these types of problems? Again, I'd like to reiterate that these investigations are exploratory, and I'm just trying to determine what the key challenges are for this type of problem, and if there are any observable features that we could use going forward to help navigate this problem space. Our first continuous benchmark problem candidate is the JY2 problem. Here we can separate two dependencies on time, one in the G function, which impacts the Pareto set, and one in the W function, which impacts the shape of the Pareto front. If we consider that these have different frequencies, there are two challenges presented to us now. The first I mentioned previously, the combination of different frequency values generates a large number of possible dynamic instances. The second one is how to report performance and take measurements when we try and solve these problems. For example, if we have different frequency for each component and we take a metric measurement just before each change, which pattern do we follow? We could measure before the T1 changes or the T2 changes or before both, or consider all three. There are arguments for all, but it's not clear yet which is the best. Let's consider a fixed severity of 0.1 and vary the frequencies of the different components. From the previous frequency severity analysis, in the heat map shown here, the highlighted row in the heat map is equivalent to the diagonal in each of the lower heat maps, where the frequency values of the two components are equal to each other. The three heat maps shown here illustrate the difference when taking measurements before each of the T values or before both. We can observe two patterns in these heat maps. Firstly, there's a pattern of better performance along the half diagonals, shown most clearly in the center plot. These correspond to instances where the frequency of one component is a factor of the other. For example, one is 10 and the other is 20. This means that some of the changes are coincidental and the overall impact is less than non-coincidental changes. Secondly, if we look at the left heat map now, there is in this background gradient of performance from left to right. This shows us that the changes in one of the components are more dominant in impacting performance than the other. In this case, changes in T1, the G function, have a greater impact. We can also note these motifs as alter as we change the severity too. We can see that the factor frequency has greater easing of difficulty. As we increase the severity, the white squares are more prominent on the high severity, and also that the dominance impact of the different components is lesser as the severity decreases. This investigation has also been carried out for other problems, the ZJZ and DMOP too. If we now look at the combinatorial examples, we can combine any of our previously defined types of changes together to produce a multi-dynamic problem here. We can verify that for coincidental changes, meaning equal frequency and multiple dynamic components, there's similar performance of different seeding mechanisms, with good solutions found on smaller problems using a variety of different seeding methods, or for larger problems, the most diverse method persists as the best. Unfortunately, I don't have enough time to explain all of these results, so I'll move on. We just see that the most diverse seeding response has the best coverage of the examined problems, which have multiple dynamic components with equal frequency. If we vary the frequencies, if the frequencies aren't equal, this means that the location changes and item availability changes occur at different times, something we might expect from a realistic scenario. Firstly, we don't know the Pareto front and we can't calculate the Pareto front. So this means we can't absolutely quote the performance. We can only show relative achievement. And this means that we can't produce heat maps in the same way. We can't also, because we can't take an absolute measurement, comparing measurements between the patterns of changes must be done carefully due to a variation in the possible achievable hypervolume. These make meaningful representation and analysis of data for these experiments difficult, and I don't yet have a solution for this. So in terms of recommendations, we want to ensure coverage of the possible instance space, so use a variety of frequency and severities for multi-dynamic problems. Make sure that conclusions are accurately conditioned on which parameters you've used. We can use those observable motifs, the factor frequency and the dominant component, to help identify and navigate the possible dynamic instance landscape. We could also consider using algorithms that seek robust solutions, or algorithms that are adaptive or aware of the changes happening in the search space. For the combinatorial problems, I just explained the limitations, but one of the key things we could do is look for or define a unachievable but estimated Pareto front to allow us for an absolute measurement. We should also define specific patterns of changes relevant to real events, perhaps based on real data, to help narrow the possible sequences of changes that we should consider. So to summarize, I feel like I've just said everything, so I'll just move on. I've said these things. We've covered all three of these sections now. I'm aware I'm very rapidly running out of time. We're nearly finished. So we've covered all three of these sections, but it's also important to consider the limitations of the work in each of these sections. Generally, the outcomes of the investigations have prompted further questions. For example, for frequency and severity, now that we've established baselines using the static algorithms and simple dynamic responses, evaluation of more complex state-of-the-art dynamic algorithms, as well as replicating previously reported performance, may reveal interesting insights. For the dynamic traveling thief problem, further development of the multi-population models, the development of existing heuristics to better handle the dynamic changes, and the exploitation of the drop rate parameter, for example, in its definition, for clever solution construction are all remaining tasks. For the multi-dynamic problems, development of an effective approach to instance selection and the potential application of instance space analysis techniques, defining features, for example, may assist in guiding experimentation further. This requires generally the development of these techniques for dynamic problems, though. Finally, investigating, if you can believe it, an even more complex case of when the frequency and severity parameters are not fixed, they're noisy or have uncertainty, applies to all three of these topics. We've produced a number of publications on the different topics, and these are shown here. I'm very much looking forward to presenting on the frequency and severity stuff at Gecko next week. Perhaps I'll see some of you there. None of it would have been possible without the brilliant Michael and also my supervisor in Birmingham, Jin Yao. Both are a constant source of encouragement and insight and feedback. So thank you very much for coming today and listening to me.